Okay, so welcome again, and we continue exploring the KiCad open source free software to design the real world electronic circuits and systems. And in that series, today we are going to design a simple voltage follower circuit using operational amplifier, or it is also called as buffer. This kind of circuit is quite useful in A to D converter, especially you want to have a high output current to drive a low impedance nodes at the output, the loads at the output. And this is also useful for an impedance matching purpose. So what you see here, you have an operational amplifier which essentially has positive and the negative as input terminals. That's why it is a differential amplifier. It has got one output. And the basic fundamental principle says that we utilize a negative feedback where we are feeding all of the output back to the negative pin. And that's why we call it as a negative feedback. So feedback factor here is 1. And since this amplifier ideally has infinite open loop gain, and now uh, practically, if we look for the manufacturer part, the gain, open loop gain, AOL of this amplifier is pretty large, in the range of 10 to the power 5 to 10 to the power 7. Because of that, we can apply the virtual short concept for the simplifying the analysis, in which we see that the voltage at the negative pin and the voltage at the positive pin are at the same magnitude or at the same level. So whatever the input you have at the positive pin, that because of this virtual short will come or appear or will be assumed to be at the negative pin as well. So if you have 1 volt here, will be a 1 volt here. There'll be a no difference between the input voltages, and that's why we have seen multiple times the amplifier gain tends to infinity, because if the gain tends to infinity, the difference tends to be 0 between the two inputs of the amplifier. So you have in input at the positive pin that comes at the negative pin. And since the negative pin is tied to the output, we see that and we say that the input voltage comes at the output. So you vary input voltages here, and that will be reflected, and the output will follow the input voltage changes. So essentially output will be equal to the input, and the ratio of output to the input is equal to 1. That's why this is a voltage follower circuit, and it has got extremely high differential input impedance, and it has got extremely low output impedance. So besides providing voltage amplification of just 1, there is no voltage amplification. So use of this circuit is to act as a buffer between output and input and provide impedance matching. And since it has got very high input impedance, it can be driven by the lowest possible signal source strength. And since it has got extremely low output impedance, it has a capability to drive any kind of load demanding any amount of current. So how to design it? Because now we are dealing with the practical design. So let's say you want to use it as a interface to A to D converter or some impedance matching network. So you need an operational amplifier. So you can choose LM7332 IC. Why LM732 IC? That I will explain you in the moment. So I will double click here, and you can see that this IC I have chosen. You can choose any other IC, but before that, I would like to show you why I have chosen this IC, because you can see that this is a dual. It means in one IC there are two such units, rail to rail input and output. So it provides full swing input and the full swing output capability up to 30 volts, wide voltage range. Okay, and then there is this high output. So it has, as I said, the output is voltage is very high, and high output current, in fact, not the voltage, high output current to drive further. And this comes in this package. So more information, you can just click this link right over here, or right over here. It will open up the new Internet Explorer web page, will take you to the datasheet of this IC. There you can explore all details of it. So I needed a model for this. So what I did, I just typed the number LM7332 on Google, and I got access to the data sheet of this. And I also got access to the SPICE model. Because we are designing a circuit, we need a SPICE model to understand its performance. We have seen it several times. So with that said, let me show you here. I click the simulation model, and I have included the SPICE model file here, and I will show you in a moment how I did that. So before that, I want to see that this part was available in the KiCad library. So I click here, add symbol, and then I will type, when the library will open, I have typed this number LM 7332. I even did not type the whole number. This IC was available. So here is the operational amplifier. Since I have recently used it, that's why it is reflecting or showing here. Since I have placed it, that's why it is showing it here. I have placed it in my schematic. So if I expand this section, unlike our previous modules or different circuit, it has got three parts, three units in KiCad. Unit A has two pins at the input, that is 2 and 3, and 1 is the output. Unit B is 5 and 6, and 7 is the output. So depends. In my current circuit on the screen, you see I need only one part or one unit. So I will place only unit U1A. If I need a circuit design in which I need to place both parts, I will do so. And third is obviously the power supply pins, the positive power supply pin, pin number 8, negative power supply pin, pin number 4. Remember, this is a KiCad description of this symbol part. So here you see that there are some details of this IC. It says that this part has been derived from LM2904, which is also dual op-amp. It comes in the DIP, SOIC, etc. packages. It is a dual LM7332 is a dual rail-to-rail input-output. So that's what we want. It's a voltage follower. So output voltage and the input voltage, there must be a large wide voltage range for both input and output. Then it provides high output current to the load it will connect. If you scroll it down, there is a link to the data sheet. You can click and get access to it. Click OK. So I have placed this part also, as you can see, and I have used only unit A. I don't need this part, so I will just press escape, or just, I already placed it, I think. So I have to, let's say, Control Z on my keyboard to undo it. Once that is done, what I did, I have chosen the voltage source. Unlike in our previous models, we have shown you all the procedure to select the voltage source. I will go to library and type VDC or VScene or VScene, and that's how. Now this source is can be DC, can be time varying with amplitude and frequency, can be AC. So depend on which analysis you want to perform, it will take any kind of voltage source. So don't get confused that I'm using a sinusoidal voltage source, but this voltage source VScene gives me facility to configure it either DC or time varying with amplitude and frequency, or AC. That's why I have chosen this. Now, the voltage supplies VCC I have used 15 volt, and VEE I have used minus 15 volt. Remember, positive pin of this voltage source is connected to the ground. That's why it is minus 15. Positive pin of this is connected to the VCC, and negative pin is connected to the ground. That's why it is a positive 15. So plus minus VCC, I'm using a dual power supply. So once I use VCC and VEE, I need to use the and connect the power pins of these IC to the respective pins. So you see I have used VCC here because V plus of op amp gets connected to VCC, and V minus of op amp gets connected to VEE. Then to the positive pin, I am applying the input signal. So that's a label. We have also told you so many times in our earlier module, you can just add a click here, add global label and select or type whatever in and choose whether it is input, output, or whatever. So input I have chosen, and then I placed it here, I placed it here. I press escape now. Similarly, I got placed VO and I said it is my output level. So you see now output is connected to the negative pin, input source is coming to the positive pin, and the voltage follower circuit is ready. So now it's time to add the spice model to this one. So as I said, I just typed this number on Google and I got access to both data sheet. I studied it, and I can use the large maximum voltage up to plus minus 30 volt, or just a single supply of 30 volt. That's why I have chosen 15 and minus 15 here. So these are values not randomly chosen, rather I have chosen them according to data sheet. That's what this IC or manufacturer part provides. Once that is done, I will now show you the I want to show you the what to say. Let me take you to the folder in which I have downloaded the model. So in the download folder, I actually got the spice model in the zip file. So this is the zip file. Then I right clicked on it and I extracted all right here in that symbol. I extracted. I clicked here extract all, and after extraction I got this folder. I double click here in that folder. Don't get confused with this MP4 font of this. It is just a notepad. So LM7332. So I right click here and I will open with choose open with notepad. So with that, you now see I have details of this spice model. It is very important to understand when you are doing a real world electronic design and you want to simulate your circuits, you want to understand each and every point. So it is the manufacturer details, and there is some look at this. This is a PSpice model that's provided, and now pinout order of this IC is first is your in plus, in minus, that is positive and negative pin of op amp. Then V plus is the positive power supply of op amp. V minus V is negative power supply, and then the output pin of the, and the sequence of these pins is 3, 2, 8, 4, 1. So you need to model, you need to actually map or match this pinout order of your model with the pins of the keycad symbols. Don't get confused. We have explained it several times. So I repeat, you want to match for, remember this order of the pins. Pin number three here is positive pin. Pin number 2 is negative pin. Pin number 8 is V plus. Pin number 4 is V minus, and 1 is the output. And in symbol of KiCad, you will have something different when you actually place that. So let me show you that. For example, you click here, and let's say I want to use the unit A again. I double click here, look at this. So I double click here and escape, and I then double click here. Oh, first I need to get rid of this small symbol. So I press escape button. Now I double click here, and here I click simulation model. Then look, when it comes to add the spice model from the file, I see the empty field. So I go click here, go to download where my file is available. I choose this and I select this. Once that is done, look at this. This model comes right here. Okay. But before I click OK, if I click the pin assignment, here are the symbol pins of your KiCad part, that is 7332. And here are the model pins that were not assigned. So it is our duty as a designer. You have to assign those pins and map the symbol pins correctly with the model pins. Okay, so I cancel it. And rather, I will show you now what I have done. So I will select it, delete it. And here for this part, I will show you now how I have mapped the symbol pin of KiCad of 7332 with the model pin of 7332. Double click here. I go to simulation model, and you see I have called the spice model from the file, and then I chose this LM7332. And when I did that, when I clicked OK actually, or when I assigned this, then I clicked here. And here there was some mismatch already, but I have corrected that, and now my symbol pins are properly matched and mapped to the model pins. Otherwise, I will run into an error. If I don't match, my simulation results will be wrong. Once I loaded the model, you see here in this text, in this box, my model got loaded. So let me just zoom in this. So here you see the pin out order. Pin number 3 is the positive pin. Now look at this first pin, symbol pin A1 is, can we see that? Let me show you the symbol pin also, because that's what we want to do it. So why not just zoom out and then double click here, and then maybe just take this box in this direction. Now I can see pins of the symbol. Then click simulation model, and now I will just take this box also this way and click pin assignment. Now symbol pin 1 here is output in the KiCad, but which pin is the output in the model? So pin 1, pin 5 actually is the, this is the pin out order. Here the sequence 5 actually is the output pin in the model. So I have chosen this 5. Okay, 5 is my model pin, which is matching with the symbol pin, that is the 1 here. And that's why in the parenthesis it is showing that 5 is matching to the 1. So 5 is the output in my model and 1 is the output in my symbol. Now 2 in the symbol is the negative pin. Now which pin is negative pin here? 2. So here is 2 in the model. Now 3 is the positive pin in the symbol. Which pin is 3? You see now, you got the 3 here. Okay, you got the, in fact, I have to tell that this is the pin number 1, which is the pin order 1, because the 3 comes the first time, first here. That's why I'm saying that it is 1 and matching with the 3. Okay. Now 4 is negative supply here, and 4 is also the negative. So that is correct. Now 5 is not connected because in symbol I don't have pin 5, I don't have pin 6, I don't have pin 7, but I have pin 8, which is VCC, and that VCC here is pin 8, which comes in the third number here, 1 2 3. So that's why it is come 3 and it is pin 8. Okay, so just try to understand it very well. If you miss to do that, your simulation results will mismatch and won't be to that. You can try that, just assign something. So it was not what it is shown now. It was messy. I corrected it, right? Okay. And then click OK. Then maybe just zoom to objects. Now you're set to run the simulation. So before that, I press ERC. I have carried the ERC, which gave me 0 error and 2 warnings. So it says that I did not place unit B, which is okay because I'm using only one part. It also says there's something related to unit B, so I don't care. So close it. Now I will just click the simulator. I will click the simulator, and once simulator is open, I will go to new analysis tab. Now there is a DC operating point analysis first. So I will get to understand voltages, currents, and the power consumption of my circuit. So if I'm looking for low power design, so obviously it will help me, but with plus minus 15 volts used, I don't have any passives such as the resistor capacitor. So let's check out how much is the voltages and the currents in the circuit. So now look at this. I got a whole range of values and parameters to understand. X stands for the components inside the uh, sub-circuit. I stands for the current from the voltage source. V5 is like about 1 milliamp, close to 1 milliamp. V1 is 1 milliamp, and then this is the X stand for inside the sub-circuit. Will increase, ignore that. Here 1 microampere from the input signal source. Because we have used the 100 millivolt. I will scroll it down. We are mainly interested in the power of V4 is 0 watt. Output voltage is minus 1.37 millivolt. So you see now you got this voltage 1 millivolt, something close to that. Because DC voltage is 0, still you got this one, but we have used the 100 millivolt. So let me do that. Let me not confuse you with that. With amplitude, why not we just, but we are using the DC and operating point analysis, so this won't be considered. So let's say I don't really care of using it. Let's say 0 frequency, I don't care. So now with that, click here, run again, and now we'll see how the results are. So power or voltage source V1 is minus 14.3 milliwatt. Power from V5 is minus 14.4. So total power is like minus 28, something like that. Okay. Plus VEE and VCC are plus minus 15 volt, and then the rest are all these circuits, sub-circuits inside the sub-circuit. So with that done, output is minus 1.3. That's an output offset voltage. Even though you don't have any difference voltage, you have this. Now look at this, is important. Input voltage is 0 volt, and the total power consumption of the op-amp is about 28 milliwatt. So 28 milliwatt, your voltage follower circuit is consuming. How about go to next analysis? We want to see whether it works as a voltage follower. So for that, we'll go for a DC sweep. Now, which voltage source we will use? Source 1, V1. Now, type is volt. Now, V1, V4, V5. So I think V4 is our input signal source. Let me show you that. Look at this. V4 is your input signal source. V1 and V5 are your power supplies. So we want to sweep this, and we'll see with these changes, output follows the input or not. Look at this. The currents and voltages have been printed or back annotated after the DC operating point analysis. Now come back here. Starting value, let's say minus 10 volt, because we have said this IC from the manufacturer. I verified from the datasheet also. It can provide you wide voltage range, both for input and output. So minus 10 to 10 volt, I want to see increment of 1 volt. I want to sweep the input voltage, and we'll see if my output faithfully follows the input or not. So let me take it down. Once I select the analysis, all signals are done here. Run it first, and room temperature simulation has been done. So let me show you. I will be plotting input signal first. To look at this 0 here. So -10 to 10, -10 to 10. So I plotted the input signal. That's the voltage. Now I am interested in output voltage here. Oh, great. Look. So faithfully output is following the input. So it's a voltage follower or buffer circuit. Okay, that's really good swing. So this is a real world design. Okay, we are not doing a generic op-amp simulation. You can really match with your specification, depends on that. So now export current plot as PNG, maybe just give it some name in the download folder and access, save it. Once that is done, I will go to click new simulation. I am interested in performing, let's say, transient analysis. Now, what kind of frequency I will apply? Maybe let's say 1 micron. Final time is, let's say, 10 micron. Initial time, I'll just keep it okay. But before that, I need to provide the stimulus in the time domain. So let's say amplitude is, let's say, 1 volt. Frequency is about now 1 mega. We'll see if that kind of high frequency it can do it. Okay. And then go to simulator again, run, and we'll see if it goes and gives me a signal. So I think this signal is not looking very clean because I have to select the fine step. So I clicked here. Instead of 1 micron, I would get 0.1 micron. Why not? And then maybe I run it again, and look, still it is better, but not what I would expect. So I will go for, let's say, 10 nano, maybe 10 nano, and let's say okay, and select and run simulation again. Now better and looking clean and crisp because I have chosen a finer step. So now look, my signal is 1 volt peak, frequency of 1 mega. Look at the output. It's very good. A very little phase difference. A little phase difference. Soon fit on screen, but output is following to input. Again, export current plot as PNG. Give some name like here and click OK. Finally, come here and we'll see that AC response, small signal analysis, number of points, let's say 1000, start frequency DC, you start with 1 hertz and let's say 10 mega. That's it. We'll see what's the unity gain frequency of it. So click here and the simulation is done. We are interested in plotting the gain and phase of the output. So where it is? Here it is, gain. Look at this. So I have a gain of 0 dB, which is gain of 1. In dB is 0. So it is giving me up to 1 mega, a constant gain of 1. So in time domain, if I go beyond 1 mega signal frequency, then I'll have a attenuation. The voltage follower won't work properly. And the phase, look at this, the phase shift is 0, perfect, up to this frequency about 100 kilohertz. And that's why in time domain we had 1 mega sinusoidal, so the phase shift was observed, a little bit phase shift. So this is the practical circuit and very nice simulation results. You can actually do that. And now look, let's say you select the color here and that's it. Okay, again you save it, current to the plot, and maybe let's say give some name and save it. So this is how you successfully design the voltage follower circuit using IC LM7332. You can use another parts also depending on your specification. If you are an electronic design or hardware design engineer, hopefully you can follow and learn and benefit from this module. So if you like this module, click the like button, share it with others for wider reach, and stay tuned for more informative modules like this. Till then, wish you a very happy learning.